Now, to drive in the point on recurrence sequences, let us look at one final example from SAJC Mid-Year Exam 2007. Okay, so please take a look at example 16. Now, in example 16, what we are given is a sequence of positive numbers. Bear in mind, positive numbers xn satisfy the relation given below. And as n tends to infinity, I am told that xn tends to a. Okay, immediately, for the more sharp students, we can also conclude that xn plus 1 must also tend to alpha. Alright, so I'm asked to find the value of alpha. So xn plus 1, now this is exactly what we have done in example 15. Okay, so let's run through the working very quickly. So I know for sure, as n tends to infinity, xn tends to alpha, and xn plus 1 must tend to alpha, right? So this means that all these I can replace with alpha. Okay, so rewriting, I basically have, after I replace all with alpha, I have alpha is equals to alpha over 2 plus 3 over 2 alpha. Now then, I can easily solve for alpha, right? So first, I bring this term over. Okay, so I have alpha minus alpha over 2 equals to 3 over 2 alpha. And so I have this line over here, okay? Alpha over 2 minus 3 over 2 alpha is, alpha over 2 is equals to 3 over 2 alpha. Now, collecting my alpha squared terms, or rather, making alpha the subject, I have alpha squared equals to 3, and so alpha equals to plus minus 3. Now be very careful, I have to reject negative. Why is this so? Remember in example 15, we also rejected one value. Why? Because the numbers are all positive, so the limit must also be positive. Okay, so that's it for finding the value of alpha. I hope that all of you will be relatively comfortable with this skill by this point in time. Now in part 2, we are now asked to show that if xn is more than alpha, then xn is more than xn plus 1. But what does this mean? Or why are we asked to show such a strange thing? I want to explain to you why we are doing this. Okay, because otherwise you will think that it's a meaningless exercise. Now what's the implications of saying that if xn is more than alpha, then xn is more than xn plus 1? This means that xn plus 1 will be less than xn, right? So that means that my value of the sequence is actually decreasing. Okay, because each subsequent term is going to be smaller than the previous term. So what this inequality here, what it means in plain English instead of mathematical symbols, okay, what it means is the sequence is decreasing. Is it decreasing all the way? No, it is only decreasing if xn is more than alpha. Okay, can you understand? So this means that, let's say my term is more than the limit, all the subsequent terms will be smaller so that it will tend to the limit. So that's what it means in words. Okay, so how do we show this? There is quite a standard way of showing. Okay, so please pay attention because this is a common type of question and we all have to be able to handle such questions when we see them. Now, there's an interesting idea here. We want to show that xn is more than xn plus 1, right? Now, instead of showing this, because this is quite a strange statement, can I actually rewrite it? Okay, if I were to bring everything to one side, do you see that it's the same as showing that xn plus 1 minus xn must be less than 0 when xn is more than alpha? That makes sense, right? So let's consider the left hand side. What is xn plus 1 minus xn? Now this suggests that there are two unknowns. Okay, xn plus 1 and xn, which makes it very hard for us to work. But if you look carefully, do you see that xn plus 1, I can actually write it in terms of xn? Okay, by using the relation given over here. Okay, what the lecturer has done is, we have chosen to write xn plus 1 in terms of xn. Please take this down. And why do we do this? This is so that we only have one variable, so that we can easily work it out. Okay, so let's simplify it. We will get to this point. Now then, what do we want to conclude about this? We want to conclude that this expression in green over here, it must be less than 0 when xn is more than alpha. Okay, so we have basically shifted our whole problem. Instead of proving this, we are now going to prove that this expression is less than 0 whenever xn is more than alpha. Now then, how can we do this? If xn is more than alpha, based on part 1, we have found that alpha equals to root 3, right? So if xn is more than alpha, then xn must be more than root 3. So let's sketch a graph. You can either choose to sketch the graph of this expression, or what I've chosen to do is, I've chosen to sketch the graph of the numerator. Okay, so if I were to sketch the graph of y equals to 3 minus xn squared, okay, against xn, I find that whenever xn is more than root 3, my y value is going to be negative. Okay, so from the graph, I see that 3 minus xn squared, the y value is going to be negative whenever xn is more than alpha. So the way I write it is, if xn is more than alpha, from the graph, I can see that 3 minus xn squared will be less than 0. So I know that my numerator here, highlighted in blue, this is going to be less than 0 from the graph. Okay, and that is when xn is more than root 3, which is for this part. What about the denominator? What about this? Do you remember that right from the start, we were already told that xn is always positive? So this one must be always positive since xn is more than 0. So 2 times of xn must also be positive. So since xn is positive, this whole expression is going to be negative. But how did we get this expression? Remember that this expression is simply xn plus 1 minus xn. Okay, so what I've done is, shifting everything back, I therefore know that xn must be greater than xn plus 1. So what is the crux for tackling these kind of questions? Let me give you a quick summary for this kind of proving question. Firstly, we translate the problem to xn plus 1 minus xn more than 0. Okay, instead of working with this. Following that, I ensure there is only one unknown. And how did I do that? I did that by doing this, okay, writing xn plus 1 in terms of xn. Now following that, what did I do? Observe the new expression and try and conclude whether it will be positive or negative. So observe. Okay, and finally, I have to rewrite it into the original form. and see that I have successfully shown. So that concludes our lectures on the limit of a sequence. In our final video, we will be looking at the limits of a series and therefore close this whole chapter on summation of a series.